All right, welcome to the unit on electrostatics. This is the first out of most likely probably 5 videos or so on electrostatics, and it's important to talk about the definition of electrostatics and what that includes. So this first video is going to serve as an introduction, and then we'll get to the math later on. So first of all, the electrostatics is the study of stationary electrical charges or fields. And so this is our very first taste into electrical charges and electrics, period. And primarily the important point there is that they are stationary. Next unit, we will get into current electricity, which is electric charges that are in motion. All right, so first of all, to get us started, we need to do a little bit of review from chemistry if you took chemistry. And if you haven't taken chemistry, then this is either new to you or you maybe have not seen this in a while. And so before we get started, there's two what we call subatomic particles we need to be familiar with, and that is a proton and an electron. Now, all matter consists of protons and electrons, and depending on how many you have of each will depend on what the charge is. We'll get to that a little bit later. But for this slide right now, all we need to know is we need to be aware of some conventions. First of all, a proton is going to have the symbol of the letter P with a plus sign because protons are positively charged. And then electrons are going to be the letter E with a negative symbol because electrons have negative charges. And then another convention just to be aware of in case you were not aware of this, like charges are going to repel one another, similar to a magnet, how the two north ends repel. And then opposite charges are going to attract to each other, just like a magnet, the north and south will attract to one another. And so that'll be important to know as we go throughout the unit, especially when we get to the math. All right. Some other definitions we need to be aware of are conductors and insulators. I'm sorry, my recording box is in front of there. There we go. Conductors and insulators. Now, you may be aware of these terms maybe from if you've ever done maybe work around the house or if you're really into electrics as a hobby. But conductors are called that because they are allowed to conduct electricity. Or another way of saying that is conductors allow electrons to move within them. So electrons are allowed to move freely. An example of a conductor, and there's many examples, but an example of a conductor is metals. We use metals in our electricity in our houses, such as copper, because metals allow electrons to move. And if electrons can move, that's how charges get transferred. Insulators, on the other hand, only have charges in fixed places. So they do not allow electrons to move, but the material is very rigid. And so the electrons end up getting isolated in only one particular spot. An example of this is rubber. Rubber can have a charge on it. However, because rubber is an insulator, that charge is not allowed to flow to all areas of the rubber material. And therefore, the charge is going to be isolated in only one spot. This is why they say that being inside of a vehicle during a lightning storm is very safe because the tires are what's in contact with the ground. And since the tires are made of rubber, if there's a lightning strike, there will be no electricity that will go up into the vehicle because the rubber is not a good conductor. It's an insulator. It's going to keep those charges in check. That's also why having good rubber-soled shoes is another good idea anytime you're working with electricity, because that will make sure you are not shocked from any sort of electrical current that could be passing through the ground. Okay, now to the main focus of this video. The main focus of this video is we're going to talk about how do things become charged. Since electrostatics is all about charges, we're going to talk about what those 4 methods are. So there's 4 ways that items can become charged, and that's as follows. There can be charged by friction, and that's when things rub together. We'll talk about that more in depth on the next slide. The second one is charged by conduction. This is where a charged object touches a neutral object. Then there's charge by polarization, and that is where there is no conduction, meaning there's no flow of charges. There's just a rearrangement of charges. And then the fourth and final one is charge by induction. And what that is that is going to be primarily only for conductors, so insulators are not in this category. And this is where neutral objects are charged and they stay charged. Okay, so we're going to go through all 4 of those more in depth so we understand what they are saying. So let's start with charge by friction. All right, charging by friction is, like I said, it's simply by rubbing 2 objects together. And I think this one's the most intuitive because we've experienced this to some degree. The example I have is rubbing material with wool. If you were to take a patch of wool and rub a material with it, you almost hear that little crackling sound, and that crackling sound is the charges that are being created. Now, what happens is these objects that are being rubbed together start out with a neutral charge. So if I were to draw, let's say you have um, a wooden, or sorry, not a wooden rod, a rubber rod, okay, rubber rod, and then you were to take a patch of wool, small patch of wool, okay, these objects are going to start out as neutral. Now, when I say neutral, that doesn't mean it has no charge, but what that means is it just has an equal number of positives and negatives, and they balance each other out. So I'm going to choose really simple numbers just for to get the point across. So let's say that my rubber rod has 3 protons. So there's 1, there's 2, and then there's 3. Now, if it only has 3 protons, it's not neutral, so it must have 3 negatives or 3 electrons equally distributed to cancel it out. So that would be a neutral rubber rod because it has equal number of positives and negatives. And I'm going to say the same thing for my wool. Okay, let's say it has 3 protons, and let's say it has 3 electrons. So they're both neutral objects because they have the same number of protons and electrons within their material. Now, when you take that wool and you rub it against the rubber rod, so you're creating friction there, what happens is the wool is going to acquire a positive charge because it gets stripped of its electrons. So what happens is these electrons that are right here, when you rub them against the rod, they get transferred over here to the rod. And intuitively at the same time, that creates a charge. And so when it loses those electrons, your wool now has a net charge that is positive because it has lost those electrons that made it neutral. And if the wool becomes positive, then the rubber rod now is negative because it has an excess of negative charges. And so that is what happens when you rub a material with wool. Now, every material is different, and certainly there are many materials in the world that we could discuss, and I'm not going to discuss all of them, but I did want to show you really quickly. There is a website here that I have pulled up. This is the effect of materials on static electricity. So I just went to a random site off the internet, and I like this one because it gives a pretty comprehensive list. So you can see right here, this is materials that tend to gain a positive electrical charge when they are rubbed together. So there's our wool. You can see some other ones, rabbit fur, dry human skin, leather, human hair, just a lot of different examples. And then if I were to scroll down, there's a list of neutral. So there's very few materials that tend to stay neutral, but there are a couple. Cotton, which is why most of our materials are made of cotton. And then these materials down here are materials that tend to gain a negative charge. And so you can read through there. You can see some examples there of materials that are going to gain a negative charge there. But that's just to show you some examples. But the idea here is we want to get that charging by friction is 2 materials being rubbed together, and the electrons are stripped from one and therefore put on the other one through that contact. Okay, the second one is charged by conduction. Now, charged by conduction is where a charged object touches a neutral object that happens to be a conductor, meaning the charges are allowed to move freely, and therefore that process ends with the neutral object becoming charged. And so here's an image that I like to use. In this first image, you have a metal sphere with an excess of negative charges. Okay, so this charged sphere right here is negative because it has an excess of negative charges, so that's shown. And it's brought near a neutral electroscope. Now, you don't need to know what an electroscope is necessarily. You just need to know that it is right now it's neutral, and it's made of metal. And so it's a conductor. Now, what happens is when that negatively charged sphere touches the electroscope, so there's contact there, the electrons are going to move from the charged sphere, and they're going to move to the electroscope and spread uniformly. Now, they are spread uniformly because the electroscope is a conductor, meaning once the electrons are allowed to make contact, they quickly spread through the entire metal object. And so you can see the result here is that the metal sphere now has less excess negative charges, because where did those negative charges go? They went to the electroscope here, and that's why the electroscope now is negative. Now notice, this is only going to work if the charged object comes in contact with a conductor, and that is because it allows the charge to spread through. All right, let's look at the final two to end our video. The final two first starts with charge by polarization. Now, if you remember, this is going to be not a spreading of charge, but a redistribution of charge. And so this does not have to be a conductor, it can be an insulator, and primarily it is an insulator. So here we have an insulated object. Okay, so it's an object that's not going to allow charges to flow, but the charges are going to be isolated. Now, this insulated object is neutral. That's what the N stand for. And remember, neutral does not mean it has no protons or electrons, but it just means it has an equal amount of them. And so I've shown 8 atoms that are in this insulated object. Obviously, there's many more than just 8 atoms, but we only need to see 8. And so right now it's neutral. There's even distribution of negatives and positives. Now, when a charged object is brought near, remember what I said, like charges repel, but opposite charges attract. And so when this negatively charged object, whatever it happens to be, is brought near this insulated object, notice what happens. There is a kind of a shift in charges. The charges are all still there, but now the positives, you can see, have aligned themselves to get as close to the negative object as possible, whereas the negative gets as far away as they can. But they can't move because it's an insulated object. So the charges are pretty much static, they're pretty much stationary, but instead of it being neutral over here, where it was probably positive and negative, pretty close to each other, they've split into positive and negative. Now, what happens if I bring this charged object away, and I bring it away from the insulated object? Well, then the insulated object would go right back to being neutral. And an example of this is if you bring a balloon, a charged balloon, close to a wall. And I'm going to show you that here in just a second. Okay, so here's an example of charge by polarization. So we take this neutral balloon, it doesn't have any charge, and we're going to rub it against this wool sweater. And we know after charge by friction that when you rub, this is charging by friction, by the way, when I rub this wool sweater with the balloon, we can see that the wool was stripped of its electrons, and now where are they? They're on the balloon. Now, if I take the balloon, which is now negative, notice the wall on the right-hand side. The wall is yellow. It's neutral, but it's neutral because its positives and negatives are evenly distributed. If I bring this negative balloon close to the wall, look what happens. Those negatives feel repelled because the balloon is negative, and so they repel each other, and so it's going to stick to the wall. So if you ever take a balloon and you rub it with wool, or even on your hair, and you give it a negative charge, you can actually stick the balloon on the wall. You don't even need any tape. You just stick it to the wall, and it'll actually stay there. And the reason why it's staying there is because it is polarizing the wall. The wall is polarized temporarily because the negative particles in the wall want to get away from the negative charges on the balloon. Now, if I take the balloon away from the wall will go back to being neutral. Okay, and also if I get the balloon near the sweater, it feels attracted to the sweater because that's originally where it had its initial charge. So the sweater is positive, balloon is negative, and so it feels drawn to the sweater. All right, and then the final way something can be charged is charged by induction. Now, this has to be done with conductors. It will not work with insulators. And so here's what is initially happening. You have object A and you have object B. They are both conductors. Now, they are neutral right now because I'm not showing any positives or negatives isolated in one spot. And so they are neutral, but they are touching each other right here in the middle. Now, what happens is I bring this negative object, maybe it's a rod, but this negative object, I bring it close to A and B. Notice it's not touching, but I bring it close. Now what happens is when the objects feel that negative object here, this negative rod, the positives are going to be isolated right here on A because all the electrons in A and in B are going to shift as far away as possible. And since A and B are conductors, and since they're touching, the negatives actually can all move over here on the right side, all on B. And so they're able to move, and transfer across A to B because they are conductors and they're touching. Now what happens is if I keep my rod close to A, but I separate A and B, I make them not touch anymore. Now A and B cannot communicate, if you will, or they cannot transfer electrons back and forth to each other. So finally, when I remove the rod completely, I remove this negative rod, the negatives would have liked to have gone back to A and neutralize out, but they can't because there's no touching. And so we now have A is a positive charge and B is an overall negative charge because they have been charged by induction. So this concludes the video on how objects can be charged. We'll see you in the next video when it gets to the math. And make sure to bring your calculator.